So, this is lecture 14, where we are going to further talk about normal mode of vibration. In the last lecture, we have described what is the physical meaning of normal mode of vibration, what is meant by synchronous motion, and how to express mathematically the concept of synchronous motion. So, in this lecture, we will take it up further and using the idea of synchronous motion, try to solve the equation of motion that we have derived to find out the response of the system. Okay. So, in the last lecture, we have seen that u1 t equal to a1 cos omega t minus phi and u2 t equals to a2 So, this two assumed solution satisfy the criteria of synchronous motion under normal mode of vibration. Okay. So, my next job, so the equation of motion that I had was m into u double dot plus k into u is equal to 0. If I write this in expanded form, I can write this as m1 0 0 m2 into u1 double dot u2 double dot plus k1 plus k2 minus k2 into okay. So, this was the equation of motion that I had. So, I must tell it here that this form of the mass and stiffness matrix that we are taking up as an example is just an example. So, if I have a different system, a 2 degree of freedom system, but with a different arrangement of spring and mass, I will have a entirely different expression for the mass and stiffness matrix. In some case, it will not be an ideally spring mass system, there I will have some equivalent stiffness and equivalent mass, and accordingly I will get a mass and stiffness matrix. Now, coming back to the solution of the problem. So, what I am going to do now is to see that if I substitute this back to this equation, is this going to be a solution of this equation, and if so, what would be the values of a1, a2, omega and phi. So, my unknown here is a1, a2, omega and phi. What are going to be the values of this, so that this is going to be a solution of this system. So, let me try to see how that can be done. So, if I substitute this into equation, I can write this as minus omega square into m1 0 0 m2 into a1 a2 to cos omega t minus phi plus k1 plus k2 minus k2 minus k2 k2 into A1 okay. So, what I have done is only substituted this solution into the equation of motion. Now, let us further check what is going to happen to this equation. I can write this as k 1 plus k 2 minus omega square m 1 minus k 2 minus k 2 and then k 2 then k 2 minus omega square m 2 and a 1 a 2 into cos omega t minus phi equals to 0, right. So, I have just simplified this first equation into this form, okay, where I have a matrix which has the stiffness term, the mass term and the omega square term, and I have A 1 and A 2 which are the two constants associated with the solution, and then cos omega t minus phi. Now, and the right hand side is equal to 0, since we have considered a free vibration case. Now, let us look into this equation. Cos omega t minus phi can never be equal to 0 for all values of time, right. For certain values of t it can be 0, but not for all values of t. So, this part of the equation cannot be equal to 0. Therefore, this part of the equation has to be equal to 0. This cannot be equal to 0 for all t, and therefore, this part has to be equal to 0 in order to satisfy the right hand side. Now, let us see what we do next. So, therefore, what we get is k 1 plus k 2 minus omega square m 1 minus k 2 minus k 2 k 2 minus omega square m 2 into A 1 A 2 is equal to 0. Now, if we go back to our engineering maths, and we can say that for non-trivial solution of A 1 and A 2, so let me write it down. For non-trivial solution of A 1 and A 2, I have to make my determinant of this matrix k 1 plus k 2 minus m 1 omega square minus k 2 minus k 2 k 2 minus m 2 omega square has to be equal to 0. Okay. Let me repeat this once more time. So, from this equation, let me call this as equation 4. So, from the one possible solution of equation 4 is that since my right hand side is 0, A 1 and A 2 both are equal to 0. That is the trivial solution. Now, if A 1 and A 2 are 0, then U 1 and U 2 are also 0. So, which is a trivial solution, which is not acceptable. So, if I want to obtain a non-trivial solution, that is a non-zero solution of U 1 and U 2, the only case where we will get a non-trivial solution for A 1 and A 2 is when the determinant of this matrix is equal to 0. Okay. If one wants to know more about this, then probably one should read the chapter on solution of equations in any engineering mathematics book. So, this let me so what is this matrix? This matrix is nothing but k minus omega square m. Okay. Therefore, right. So, we initially had a k matrix and then we did minus omega square m matrix. So, this can also be written as determinant of k minus omega square m, this matrix is equal to 0, or which actually can be written as determinant of k minus omega square m equals to 0, right. So, we have taken a particular form of k and m for a given system. If we take any arbitrary k and m for any given system, then the equation in a generic form is going to be determinant of k minus omega square m is equal to 0. Now, we see that this solution. So, for this particular case, this k matrix is 2 by 2, this m matrix is 2 by 2. I can solve this equation. It's very easy to solve this matrix equation, the determinant of this matrix, and I will get two solutions for omega square. I will get omega square 1 and omega square 2, omega 1 square and omega 2 square, because my k and m matrix are 2 cross 2. If I have a, so let me explain this. So, everything boils down to this equation, that k, determinant of k minus omega square into m is equal to 0. So, one can solve this. If I solve this, I will get omega 1 square and omega 2 square. That is because my k is 2 cross 2 and m is 2 cross 2, and it is a 2 degree of freedom system. So, if I have an n degree of system where n is 10, 5, 20 or 100, then I will have n solutions for, so let me so if I have an n cross n system, is my my k is n and my m is n, then I will have n solution. I will have omega 1 square, omega 2 square, so on till omega n square for a n degree of freedom system. Now, you will see, if you solve this system, the values for omega 1 square and omega 2 square, irrespective of the system that you are dealing with, is always going to be greater than 0, because my k is a positive definite matrix, my m is a positive definite matrix. Therefore, my solution of this equation always is going to give me positive omega 1 square and positive omega 2 square, and so for the case of an n degree of freedom system. All the solutions are going to be positive, so that the root of this solution is going to be a real number. Therefore, so now I have got the values of omega. So, omega is going to be therefore is going to be omega 1 and omega 2. These two are of course going to be real numbers. Okay. Therefore, my solution can actually be written as u1t, which is a1 cos omega t minus phi, and u2t, which is a2 cos omega t minus phi. Okay. Out of that I now know omega. So, omega is omega 1 and omega 2. So, my next job is to find out A 1 and A 2. So, once we determine omega, we can now easily say that k minus omega square m, I always have this equation which is A 1 and A 2, and that is equal to 0. So, what I am going to do, I know the solution of omega. So, I will plug in the solution omega 1 square, and therefore, I can solve A 1 and A 2, and I will get the solution as say A 1 1 and A 2 1. Similarly, if I plug in the value of omega 2 square here, I will get another solution for A 1 and A 2. Let me call this as A 1 2 and A 2 2. Therefore, what do we see? We see that the solution u 1 t and u 2 t, if I write them as vector form, is going to be A 1 1, A 2 1 cos omega 1 t minus phi 1 plus this is one solution. This is one solution. The other solution that I get is A 1 2 and A 2 2 into cos omega 2 t minus phi 2. So, these are the solutions that we are going to get. So, this is one possible, therefore, this is one possible solution of u 1 u 2, and this is another possible solution of u 1 and u 2. So, this is called normal mode 1 solution, and this is called normal mode 2 solution. Okay. Therefore, we can see that the entire, so now let us see what is happening physically. So, this is one possible normal mode vibration of the system. Okay. This solution is satisfying the equation of motion as well as satisfying the condition of synchronous motion. Similarly, this is another set of solution which is satisfying the equation of motion as well as it is satisfying the criteria of synchronous motion. So, this is a allowable normal mode, this is another allowable normal mode solution. Okay. And both of these are solution of the equation of motion. Therefore, these are acceptable solution of equation of motion under normal mode of vibration. Now comes the physical significance of normal mode of vibration. The significance of normal mode of vibration is that, any arbitrary solution u 1 t, I can in fact delete. Okay. So, this is my normal mode 1, this is my normal mode 2, and both these are allowable solution of the equation of motion. Now, the beauty of normal mode of vibration is that any arbitrary solution or response of the 2 degree of freedom system. Okay. So, if I have any 2 degree of freedom system, or to say any n degree of freedom system or any multi degree of freedom system, I give them any initial excitation possible, any initial value of displacement, initial value of velocity, then I can always say that the response of this of the system, of any arbitrary system under any given initial condition can actually be written as linear combination of the normal modes of vibration. I would like, because this is a very important concept, I would like to emphasize on this. So, what we have done till far, we have said that there is a special, let us assume that there is a special form of vibration or a special form of response of a system, which is we are calling as normal mode of vibration. So, what is the definition of normal mode of vibration? The definition of normal mode of vibration is that under normal mode of vibration, a system is going to have synchronous motion. That is, the deflected shape of the system is going to remain, the shape of the deflected system is going to remain constant with time, okay, which can be expressed mathematically as the ratio of the two degrees of freedom at any instant of time is going to remain constant. From this definition of normal mode of vibration and then following certain mathematical steps, we have derived what would be the expression, how will the normal mode of vibration look like, or what will be the expression of normal mode of vibration. We have seen that the normal mode of vibration is going to look something like this, which is going to be a constant into a cosine function, another set of constant into another cosine function. So, each of these cosine functions are going to have a frequency omega and omega 2. We know how to find out omega 1 and omega 2. We also know how to find out this constant a 1 and a 2. Now, the most important part is that if I take any system, any multi degree of freedom system and give them any possible initial condition, then the response of the system is always a linear combination of the normal modes of vibration. So, it is always going to be a linear combination of normal modes of vibration. So, any arbitrary u1 and u2 can actually be written as C1 into A11 into A21 into cos omega 1 t minus phi 1 plus C2 into A12 into A22 into cos omega 2 t minus phi 2. Therefore, this can also be said that C1 into first normal mode or normal mode 1, normal mode 1, and this is C2 into normal mode 2. Okay. So, this is my normal mode 1 into this is my normal mode 2. So, what I do, I say that C1 into normal mode 1 plus C2 into the response in normal mode 2. So, this is nothing but a linear combination of normal mode 1 and normal mode 2. This expression is very important, and this is also called as the mode superposition theorem, which we will talk in much detail later. Now, let us see how this. So, now what happens is that I know A1, A2, I know in this case as well as this case, I know omega 1 and omega 2. Now, given I will have 4 initial conditions, that is 2 displacement, I will have I will know u1 0, I will know u2 0. This should be given to me. I will also know u1 dot 0 and u2 dot 0. This also will be given to me. Okay. So, the set of initial conditions are going to be given to me. So, from those set of equations, I can always solve this 4 unknowns C1, I can always solve this 4 unknowns, which is C1, Phi1, C2 and Phi2. So, I have 4 initial conditions. These are my initial conditions that have to be known, and from this 4 initial condition I can find out C1, Phi1, C2 and Phi2, and once they are known, my entire response is known. Now, let us see what does this physically mean. So, if I have a 2 degree of freedom system under some initial condition, the response is going to be a summation of 2 cosine functions with frequency omega 1 and omega 2. Therefore, omega 1 and omega 2 are called the natural frequencies of the system. Okay. And A1, A2, this one and this one are called the mode shapes of the system. Okay. Let me just talk about it in more detail. Okay. So, I said that u1t and u2t can be written as C1 into A11, A21 into cos omega 1 t minus Phi1 plus C2 A1, A2, 2 cos omega 2 t minus Phi2. Okay. So, what does this expression would look like? This is just nothing but the 2 cosine linear combination of 2 sinusoidal functions which are vibrating at frequency omega 1 and at frequency omega 2. So, these are called the natural frequencies of the system, similar to my single degree of freedom system. And this 2, what does A1 and A2 represent? A1 and A2 are going to represent the shape of the deflected system at any instance of time. So, therefore, these are called mode shapes. Because this denote the deflected shape, because they are associated with the deflected shape, this vector containing A1 and A2 are called mode shape, and this therefore is also called the mode shape. So, we have already know how to find out omega 1 and omega 2. So, we know how to find out the natural frequency. So, for each omega I can find out A1 1 and A2 1, which I will abbreviate as R1, which is my mode shape 1, or the mode shape corresponding to the natural frequency omega 1. Similarly, for the natural frequency omega 2, I will get A21 and A22, which I will abbreviate as R2, and this is another mode shape which is corresponding to the natural frequency omega 2. Okay. So, now out of this two natural frequency, the lowest one is called the first natural frequency, the lowest of omega 1 and omega 2 is called the first natural frequency or the fundamental frequency, and the next one is called the higher one, higher of omega and 1 omega 2 is the second natural frequency. Okay. Right. So, so let me summarize what we have learned is that we have said we have found out how to find out what is normal mode of vibration. We have seen that any arbitrary response is a linear combination of the normal modes of vibration. We have seen that the arbitrary response of a 2 degree of freedom under any given initial condition is going to be a combination of sinusoidal functions with the frequency of omega 1 and omega 2, which are called the natural frequencies. We know how to find out the natural frequency. We find out the natural frequency by equating the determinant of k minus omega square equal to 0. For each natural frequency, we can find out the mode shape of the system. So, what I wish to do next is just to quickly say how this can be extended to a multi-degree of freedom system. So, we have done it for a 2 degree of freedom system. Let us see how it can be extended to a multi-degree of freedom system, which is pretty straightforward. So, as you can assume that as you can appreciate that for 2 degree of system, I had two natural frequencies omega 1 and omega 2. For n degrees of freedom system, we already have talked about this. We will have n natural frequency and we have to arrange them in increasing order. The lowest one will be called the first natural frequency and so on. So, corresponding to each natural frequency, I will have a mode shape. So, for a n degree of freedom system, I will have n mode shapes, which I will represent as R n. Okay. So, in 2 degree of freedom, we have 2 mode shape. In n degree of freedom, we have n mode shape, and for an n degree of freedom system, the total response u1t, u2t and so on, there would be n degrees of freedom. So, unt is going to be a linear combination of this n normal modes. So, C1 R1 into cos omega 1 t minus phi 1, and then I will have C2 into R2 into cos plus Cn into Rn into cos omega n t minus phi n. Okay. So, the essential difference between a single degree of freedom system and a multi degree of freedom system is that in single degree there was one natural frequency, in multi degree of freedom system there would be the number of natural frequencies is going to be equal to the number of degrees of freedom, and the concept of mode shape is new to a multi degree of freedom system, which is not there in a single degree of freedom system. So, and the concept of normal mode of vibration is also new to a multi degree of freedom system. So, with this we will end in this lecture. In the next lecture we will again continue with the solution of a 2 degree of freedom system. We will solve an example to clarify the concepts. Thank you.